All right, let's get into it. Today, we are going to pull back the curtain on one of C++'s most powerful and, yeah, let's be honest, sometimes pretty confusing features, the virtual function. I promise, by the time we're done here, you'll see exactly how it makes true runtime polymorphism possible.
So here's our game plan. We're going to start with a quick look at the hidden this pointer, because you really need to get that first. Then, we'll uncover a super common problem you run into with function overriding and see how the virtual keyword just solves it. After that, we'll cover the rules, level up to pure virtuals, and finally, we'll put the whole thing together in a complete program.
Okay, first things first. Before we can even begin to talk about virtual functions, we have to understand this other piece of C++ that's always working behind the scenes, the this pointer. Think of it as the invisible glue that holds every method call to its object. So what is it really? Well, you can think of the this pointer as this secret argument that the compiler sneaks into all your member functions. It's always pointing to the specific object that's making the call. It's basically answering the question, hey, who called me? It's the key that connects a function to its own data.
And this isn't just some weird academic idea. It has incredibly practical uses that you'll see all the time. You use it to tell the difference between a function parameter and a class member when they have the same name. Use it to chain method calls together, which looks super clean. You can even use it to compare one object to another or to just pass the current object to some other function.
And this right here makes it all crystal clear. Look at application 1, that this their name equals name, that's how you solve that naming confusion perfectly. And in application 2, see how it's returning star this? That's the secret sauce that lets you do that slick, chained call, s.setNameAlice.setMarks90. So yeah, this is stuff you'll actually write.
All right, now that we've got the this pointer down, let's set up the central conflict, the very problem that virtual functions were created to solve. Let's call this one a tale of two bonuses.
So, first off, we need to be on the same page about function overriding. This is a totally standard thing in object-oriented programming. It just means a child class can provide its own special version of a function that it got from its parent, or base, class.
And this analogy just makes it so easy to understand. You've got a general rule for every employee, but managers who are a specific kind of employee, they get their own, better rule. The manager's rule overrides the general company policy. Simple as that.
And here's what that story looks like in actual code. We have our base employee class with a calculate bonus function that gives 10%. Then we have a manager class that inherits from employee, and it overrides that function to give a much nicer 30% bonus. Makes sense, right?
Now, if you call a calculate bonus on a plain employee object, you get 10%. Call it on a manager object, you get 30%. Everything looks like it's working exactly as you'd expect. But here's the kicker. What happens if we try to use a base employee pointer to point to a manager object? This is where things get weird. And this right here, this is the absolute heart of the problem. Without the virtual keyword, the C++ compiler decides what to do at compile time. It looks at your pointer and says, oh, that's an employee pointer. I'm calling the employee version of the function. It totally ignores the fact that at runtime, it's actually pointing to a manager. This is called static binding, and it's not what we want here.
So that brings us to the solution. And it's just a single keyword that fixes this entire problem and unlocks the real power of polymorphism in C++.
Just look at how simple this fix is. In the code on the right, the only thing we changed, is we added the word virtual right in front of the calculate bonus function in our base employee class. That's it. One word changes everything.
And here is the proof. With that one little change, we run the exact same code, and we get the right answer. Manager bonus, 15,000. The compiler now waits until the program is actually running. It checks what kind of object is really there, and it calls the correct overwritten function. That is runtime polymorphism. That's dynamic binding.
Okay, so now that we get the what and the why behind virtual functions, we got to go over the rules of the road for using them the right way.
Think of this table as your cheat sheet. Remember, you only need to put virtual in the base class. Once it's virtual, it stays virtual all the way down the family tree. Also, this magic only works if you're using a base class pointer or a reference. Now, pay attention to Rule 4, because this one is a huge deal. If your class has any virtual functions, you absolutely must give it a virtual destructor. Why? Because if you don't, and you delete a derived object through a base pointer, Only the base part gets cleaned up, and you've just created a memory leak. It's a classic C++ trap.
So a regular virtual function says to the child classes, hey, you have the option to override me. But what if we want to change that? What if we want to make it mandatory? What if we want to define an interface that all child classes must follow? Well, that's where we level up. And this is a pure virtual function. You make one by adding =0 at the end. This tells the compiler two very important things. First, this function has no code here in the base class. And second, any class that inherits from me must write its own version of this function. It's not a suggestion anymore, it's a contract.
This slide lays out the difference perfectly. A standard virtual function gives you a default behavior that you can override if you want to. A pure virtual function gives you no behavior at all. It just defines a rule that you must follow. And here's the big takeaway. The second you add just one pure virtual function to your class, it automatically becomes an abstract class. And that means you can't create an instance of it directly anymore.
All right, time to bring it all home. Let's see all these ideas, virtual functions, pure virtuals, and abstract classes, all working together in one complete program. So here we go, we're defining our contract. The shape class has a pure virtual function called print. This is what makes shape an abstract class. You can't just make a shape object. It only exists to say, hey, anything that wants to call itself a shape has to know how to print itself. And then the rectangle class comes along, inherits from shape, and it fulfills that contract by providing its own print function.
And this slide right here shows you the real power of this design. We've got a cube class that inherits from rectangle. Now, look closely at our main function. Notice what we're not doing. We're not using rectangle or cube pointers. We're using shape pointers. Both of our pointers are of type shape star, but one points to a rectangle and the other points to a cube. This is polymorphism in action.
And the result? Well, it speaks for itself. When we call print using those base shape pointers, the program at runtime figures out the right function to call. It calls the rectangle's version for the rectangle object and the cube's version for the cube object. We've built this beautiful, flexible system all based on a common interface. Perfect.
So we've gone all the way from the hidden this pointer to a fully polymorphic program using abstract classes. The really crucial thing to take away from all this is that virtual functions let you write code that just cares about a base interface without needing to know anything about the specific details until the program is actually running. So the final question is for you. Where in your own code could you use an abstract contract, like shape, to make things simpler, more flexible, and easier to maintain? Thanks for tuning in.